This question is exercise 1.6.1. It is based on linear operators. So it says an operator omega is given by the matrix So the question is, what is its action? So now before we proceed, we need to know the definition of linear operators. So we have the following definition for linear operators. So a linear operator denoted by omega linear operator omega basically transforms a given vector into another vector. So an operator omega is a linear operator and it's basically an instruction for transforming any given vector v into another vector v prime. So this is the definition of a linear operator, and this is how we see its action. Its action is basically transforming a vector into another vector. Now, linear operators can be represented as matrices. So we do have the matrix representation of linear operators. So in this given question, we have this operator omega, which is represented by this matrix. So the matrix representation of this equation, that is, we have v prime is equal to omega times v. The matrix representation of this matrix representation is given as follows. We have the components of the vector v prime. So the components of the vector v prime are given as follows. Then we have the matrix for omega. This is the matrix for omega, and then we have the components of the vector v. So this is the matrix representation of the linear operator. Here the vectors 1, 2 and so on up to n are the basis vectors. So this matrix representation is basis dependent. So given a basis, given the set of basis vectors for a vector space, the linear operator can be written in that particular basis, and the matrix representation would be basis dependent. This is just like any other vector components. So these vector components, these are also basis dependent. Similarly, this matrix for omega, this is also basis dependent. So all of these are basis dependent. So let us now come to our question. So in order to find the action of an operator, we need to operate this omega on each of the basis vectors. So since an important point to note over here is that if we have n dimensional basis, that means n basis vectors. So n basis vectors means n dimensional. So n basis vectors means n dimensional space. So that will give us an n squared matrix for the operator. We see that this matrix for omega has the dimensions n squared. So our given matrix is, let us now solve this question. Our given matrix has the representation, has the following matrix representation. So this has dimensions 3 squared. So that means this is for a 3-dimensional space. So in 3-dimensional space, we can select the basis as a basis for 3-dimensional would be as follows. The first basis vector being 1 0 0, second basis vector being 0 1 0, and third basis vector 0 0 1. Notice that all of them have unit magnitude and are orthogonal to each other. So thus they are orthonormal to each other, this particular set of bases. So this particular set of basis vectors 1, 2 and 3 form an orthonormal set of basis vectors. Now in order to find out the action of omega, we need to find out how this omega acts on each of the basis vectors. So let us now find that. So omega acting on 1 is as follows. This is nothing but the second basis vector. Omega acting on second basis vector is this is nothing but the third basis vector, and finally omega acting on the third basis vector this is nothing but the first basis vector. So let us just summarize what our action is. So this is our action. Notice that this action basically tells us the column of the matrix representation for the operator. So if we see, for example, we see that omega acting on the first basis vector takes it into the second basis vector. So omega acting on 1 0 0 takes it to 0 1 0, and this is the column 0 1 0 that we have in the matrix representation for omega. Next, if we look at the action on the second basis vector, so omega acting on second basis vector takes it to the third basis vector 0 0 1. We see this is the second column of the matrix representation for omega. Finally, omega acting on the third basis vector takes it into the first basis vector 1 0 0, and this we see here is the third column in the matrix representation for omega. So this solves this question. We have found the action of the linear operator omega by finding how it behaves with the basis vectors of this space.